Hello there, thanks for watching and I appreciate you. This is a video in a series of videos showing you how to make a custom character controller that uses rigid body physics, cinemachine cameras, Unity's new input system, and custom player gravity. In the last video, we had some fun with Unity's physics by adding a reaction force to any rigid body that's under our player's feet when we jump. In this video, we'll be adding the ability for our player to ascend and descend stairs, adding stair handling basically. Sorry for the wait on this video. I ended up scrapping what I originally coded and completely revamped the code. I actually finished this a couple weeks ago and now I gotta try to remember what I did and how it works. Real life has also been getting in the way of me recording this video, but it is the single most requested video I've gotten, so I wanted to be sure to take some extra time to ensure that there's some quality to it. Anyway, I've had some time to do a bit of testing with the new code and it's not perfect, but it's a great starting point and I'm pretty happy with it so far. That said, we have a lot to go over in this video, so without any further delay, let's get right into it. As usual, we're going to start off with our character controller project exactly as we left it in our last video. If you're new to these videos, this is a video in a series of videos, so there may be some things I've already explained in previous videos that I'm just not going to spend the time to go into detail in this video. But when it's relevant, I do try to give a reference to a video that I did explain it in. So now let's go ahead and down in our project panel, under scripts, controllers, let's open up our humanoid land controller. This is actually the only script we're going to be making changes to in this video, but it is going to be a lot of changes. As usual, I'm just going to type it all in, and then we'll break it down and review it line by line. And we'll scroll back to the top so we can do some review. And we'll zoom in real quick before I once again forget. That ought to be good. Alright, before we get into this code, I just want to backpedal a little bit, talk about stair handling itself some more. There are a lot of different ways to handle this. This is not the one and only way. It's simply the way I chose for this character controller because this is a physics-based character controller that reacts to physics-related events. As such, I want this character controller to react to its environment as best as it can. So to do that, I wanted this controller to be able to detect stairs and not rely on a tag or a specific type of game object, etc, etc. I also didn't want to set up some sort of script that would detect stairs in the map and basically paste a slope over top of them so that stairs would be treated the same as a slope. Although we are sort of using a similar implementation as that because we are sort of treating stairs as slopes. But anyway, let's start going through this and we'll start breaking it down as we go through it. Okay, right off the bat, we're going to be using a list later in this, so we have to add our using system.collections.generic right at the top here. Next, this is just a little change. I made our player move input a serialized field so that we can view its values in the inspector panel. This has been very useful to me for debugging purposes. Next, in our ground check section, I renamed ground check distance to ground check distance tolerance, and I added a float called player center to ground distance. In the gravity section, we changed gravity fall current and gravity fall min to both have default values of 0. And we completely removed the gravity fall max and gravity fall increment amount variables. We changed our gravity calculation around a little bit. I just wanted to make it a little cleaner. And we'll see more of that in just a minute. Scroll down to the stair section here. There's a lot here, so we're just going to gloss over it real quick for now. In the first line, we have a float called max step height. We're making it 0.5 or half a unit, half a meter, whatever you're calling your units. In the second line, we have another float called min step depth, and we're making that 0.3 or 0.3 meters. Next, we have a float. It's called stair height padding multiplier, and we set to 1.5. Following that, we have a bool called is first step, and we're setting it to true by default. And we have another float called first step velocity distance multiplier, and we set that to 0.1. We have two bools, one's called player's ascending stairs, and the other is called player is descending stairs. They're both set to false. And we have a float called ascending stairs movement multiplier, as well as another float called descending stairs movement multiplier. We set the ascending stairs movement multiplier to 0.35 and the descending stairs movement multiplier to 0.7. Following that, we have another float called maximum angle of approach to ascend. We set that to 45, which means you cannot be approaching the stairs at more than 45 degrees of angle. If you are, you cannot go up the stairs. If you have less than 45 degrees of an approach angle, then you can go up the stairs. Depending on your game, you'll want to change this number. You probably really want it, I just said 45 because it's an in-between number, but you probably really want to be between like 60 and 75, maybe an 80, I don't know. Just play with it, and whatever works for you works, so no problem. Next, we have a float called player half height to ground. Set that to 0. Next, we have another float called max ascend ray distance, as well as a max descend ray distance for both setting those at 0. And there's some notes here, just saying these are calculated in the awake function. We'll talk more about that later. Next, we have an integer, and it's called number of step detect rays. We're setting that to 0. And then last but not least, we have a float called ray increment amount, and we're setting that to 0 as well. Alright, I know that was a lot, but hang in there. We're going to keep going. I'm going to scroll down some more here. In the jumping section, all we changed here was we added multiplier to our initial jump force variable. Originally, it was just the initial jump force, but it makes more sense to add the multiplier to the end, so it's just a little name change there, so it's a little clearer. And then down here in the awake function, we added these 4 lines, which are just assigning calculated values to our 4 variables: max ascend ray distance, max descend ray distance, number of step detect rays, and ray increment amount. Again, I know this looks terribly confusing, but we'll come back to these when they're relevant and when you understand what exactly is going on with the rest of what we're doing, so that you can see how these fit in. So let's keep going down. We'll check our fixed update loop next. In our fixed update loop, all we did is we added this line right here, player move input equals player stairs, and we also added this debug.drawRay just so we can visualize things a little bit better to help with debugging. Let's scroll down to our player ground check function now. In our player ground check function, we changed quite a bit. We are no longer returning the result of our actual sphere cast. Instead, we are comparing some values together to see if they're within a range, which is our ground check distance tolerance range. If you've been following along, you can compare this code to what we had before. Otherwise, we'll come back to this later when we talk about it more in depth. Moving on, next we have our player stairs function, as well as our ascend stairs and our descend stairs functions. Once again, we'll come back to these. Right now, I just want to cover all the little changes that we made in the rest of the code, and then we can focus on these functions themselves. Next, we have our player slope function. In our player slope function, instead of just checking to see if the player is grounded, we also check to see if we are ascending stairs or descending stairs. If we are ascending stairs or descending stairs, we do not want to check to see if we are on a slope. Next, we removed our float called ray height from ground. We deleted that, and we're no longer using that variable. Instead, we're using our new variables that we set up called player center to ground distance, and we're adding that to our ground check distance tolerance to find out what our ray calculated ray height should be now. Again, this will make more sense later. Let's just not get hung up on this little stuff for now. I just want to get through these changes so you know what to change in your code. So let's keep moving. Next, I commented out this debug.drawRay for now because we don't need this here. And if we keep scrolling, I also commented out this entire if Unity editor debug drawRay check if statement. You can just delete this if you like. We don't need this anymore for now. Continuing on to our player fall gravity function, we changed quite a bit here. Right off the bat, same as our player slope function. In addition to checking to see if our player is grounded, we're now also checking to see if our player is ascending stairs or descending stairs. If we aren't doing any of those, then we are not falling, and we want to reset our gravity fall current to a gravity fall min. If you remember before, we had the global variables gravity fall max and gravity fall increment amount, which we both removed. They are no longer global variables. We have made them local variables within this if statement. Because I got a little carried away with this, I went ahead and changed this so that it would calculate itself based off some of our other relevant variables. This is very rudimentary, and you would not want to leave this for final results, but it's just something to play with. Also, our next if check here, if gravity fall current is less than gravity fall max, before that was greater than, we changed that now to less than. Make sure you change that, because now we're dealing with positive numbers. And at the very end here, down here where gravity equals negative gravity fall current, we are making the gravity a negative value again by setting our gravity fall current to a negative value. In our player jump function, don't forget to update initial jump force to our initial jump force multiplier variable. But that's all that was changed here, and with that, we are done with the initial review of the code. Now we have that out of the way, let's get into the meat and potatoes here. We're going to scroll up. If you remember, our player stairs function gets called within our fixed update loop, within our player stairs function, and in our first line, we're creating a local vector3 variable called calculate step input to temporarily store our player move input. Once we're done modifying this, we're going to return it. As I've said in many videos before, this is just that we can have a local variable to modify before we return it. It just makes it easy so that we can go into our fixed update loop and see what is modifying what. When you're using a lot of global variables that are getting modified in various different functions, it can be hard to follow the flow, and this is just a little step I like to take to help make more sense of it. In this block of code here, we're setting our player half height to ground. We'll get into why this is important later. So moving on to the next line, we're taking our vector3 calculate step input, and we're saying that equals the return value of our ascend stairs, and we're passing in our calculate step input. If our player is not ascending stairs, then we're going to do the same thing, except we're going to check to see if we're descending stairs. Obviously, if we're ascending stairs, we don't need to waste the resources on checking to see if we're descending stairs, so it makes sense to just execute one and not the other. And finally, we're returning our calculate step input. Let's keep going and scroll down to our ascend stairs function. Unfortunately, because we're zoomed in so far, some of our lines are too wide to fit into our viewport. To resolve this, I'm just going to close all the windows that we don't need so that we can see everything. Okay, that's much better. We can see the entire line of code now. I want to take a moment to give some words of encouragement because this next bit may be a bit much for a lot of people viewing this. Don't get discouraged. I'm going to brush over this code somewhat quickly, and I expect most viewers will get a little lost. Right after we're done here, we're going to jump right into a playtest where I'm going to demonstrate the code working. Then finally, we will do a more in-depth look at the code and how it works, along with a bunch of your favorite drawings. And as always, if you have any questions, please feel free to ask them in the comments. I've enjoyed interacting with you all, and I'm happy to try to answer any questions you may have related to this character controller. All that said, let's get back to the code. In our ascend stairs function, the first line, we're checking to see if our input.move is pressed. So basically, if we are pressing a movement key, then we're going to create a float called calculate vel distance. If this first step equals false, then our calculated vel distance is going to equal our capsule collider radius. Otherwise, if its first step equals true, then our calculated vel distance is going to equal our rigid body velocity magnitude times our first step velocity distance multiplier plus our capsule collider's radius. Basically, we're trying to get a distance value that's relative to the velocity at which our player is traveling. This is not a great way to do this at all, but this is a simple way. This is very inefficient and just not very accurate, so it's not a good way. You don't have to do it this way. Feel free to improve this. It should be improved, but for now it works. You don't want to get hung up in trying to optimize and make code perfect. It's best just to get it out there, get it working, and you can improve and optimize it later. Just don't get too caught up in trying to make things perfect that you don't ever actually make any progress. Moving right along, next we're going to have a float. We're calling it array, and its initial value is going to be 0. After that, we're creating a list of raycast hits called raise that hit, and we're initializing it as a new list of raycast hits. Next, we are starting a for loop, and we're creating an integer called x. We're setting its initial value to 1. If x is less than or equal to our number of step detect rays, then we're going to increment x by 1, and we're going to add our ray increment amount to our ray float. In our actual for loop, we're creating a vector3 called ray lower. We're creating a new vector3 with basically our player's location minus our player half height to ground, so we're getting where our player is meeting the ground, and to that we're adding our current value of our ray float. Next, we're creating a raycast hit called hit lower to store our raycast hit information within. And finally, we're doing an if check to see if our raycast actually hit anything or not. We're sending the raycast out from our player position that we just created called ray lower, and we're sending it in the direction of wherever we're telling our player to move. We're storing the hit information in our hit lower raycast hit that we just created, and we're sending out as far as our calculated vel distance plus our max ascend ray distance. If this raycast hit actually did hit something, then we're going to create a stair slope angle, and using Unity's built-in vector3.angle function, we're going to find out the angle between our hit lower.normal and our rigid body transform up. If the angle ends up being a perfect 90-degree angle, then we're going to go ahead and add this hit information to our raise that hit list. We'll scroll down a little bit here. If we have at least one ray in our raise that hit list, then we're going to create a vector 3 called ray upper, and we're going to create it again at basically our player's location, except we're going to change the vertical position to be minus our player half height to ground, plus our max step height, plus our ray increment amount. We're then going to create a raycast hit called hit upper, and next we're going to send out a raycast starting from our ray upper vector 3 position, and we're going to send it in the direction of our player move input. We're going to store any hit information in our hit upper raycast hit variable that we've created, and our ray travel distance is going to be our max ascend ray distance times 2 plus our calculated vel distance. Next, I'm just going to gloss over this code very quickly. If our upper raycast hit did not hit a collider, or if our distance between our lower raycast and our upper raycast is greater than our min step depth, then we're also going to check to see if our angle of approach is less than or equal to our maximum angle of approach. If so, we're going to draw a debug.drawRay just so we can visually see where our upper ray is being cast. Next, we're finally going to say that our player is actually ascending stairs by setting our player ascending stairs boolean to true. After that, we're creating a vector 3 called player rel x, or player relative x, and it's going to be the cross product of our player move input and a vector 3 up, or you could do our player transform up. This next part is not very clean code at all, I'm not proud of it, but it does work for now. We have an if statement checking to see if first step is true or not. If it is true, then we're going to say calculate step input equals Unity's built-in quaternion function called angle axis, which basically creates a rotational value. We can rotate any number of degrees along any axis. So in this case, we're going to rotate 45 degrees up along our player rel x axis, and we're going to multiply that by our calculate step input in order to modify our calculate step input by that amount. And then we're going to set is first step to false, so that next time we come through, this is not the first step anymore. Let's scroll down just a little bit. If not is first step, then we're going to create a float called stair height. It's going to equal the number of rays that hit times our ray increment amount times our stair height padding multiplier. After that, we're going to create another float called average distance. We're going to set that to 0. We're going to add all of the distances from our raycast hits in our list of rays that hit together and divide them by our total count so that we can get an average distance. And using all of these values, we're able to create another float called tan angle, and we find out the tangent angle needed for our player to get from the bottom of this stair to the top of the next stair. And then same as before, we're just going to adjust our calculate step input to take that into account along our player rel x axis. And then finally, we're going to also apply our ascending stair movement multiplier to our calculate step input. This should probably also be applied in our is first step one as well. But, you know, little details don't really matter a whole lot. It's just going to be calling for one physics loop, so it's kind of optional. But we're in the home stretch now, so let's keep going. Scroll down a little bit more. We have all of our else statements down here. I have commented what each else statement is for, but in each else statement, we're just going to say our player ascending stairs equals false and is first step equals true. So these are basically just a reset. Again, I know this is kind of messy, but it is all there for a reason, and it just kind of lays it out in a simple way that is easy to understand and follow. And finally, if I scroll down a little bit further, we have our descend stairs function, which is very similar to our ascend stairs function. And in a perfect world, these probably should not be separate functions, or if they are separate functions, they could use functions that have the same code in them, so that we don't have a lot of duplicate code. But I wanted to keep this kind of modular so that you could see how they are separate from each other. And I just think it's easier for a newer person to this type of thing to follow this type of code. But this is not good code, this is not good practice. But anyway, instead of typing this all up, it's probably going to be easiest to do what I did, and I copied the ascend stairs function and pasted it again, and then modified it from there into the descend stairs function. Again, these functions are very similar, so I'm not going to go over it line by line. You can see it on the screen here, and you can stop, pause the video, and copy what you need. Also, I forgot one little change. If you stuck through this and watched all of this through, then this might save you some headache later. If we scroll down, to our player info capture function. This function is no longer going to work properly since we changed our player ground check. We are no longer determining whether we are grounded depending upon whether our sphere cast hits the ground or not. Instead, it's going to almost always hit the ground as long as there's ground somewhere below us because we're sending it an infinite distance. Instead, we now need to check see if our player is grounded, and then we can check to see if our ground check hit has a collider or not. So this is a pretty simple solution. We'll just go ahead and add the player's grounded check here in our if statement, and this will be resolved. Okay, now with this all finally done, we're going to jump back over to Unity and we're going to add some stairs for our player to traverse so we can test them. Okay, let's test our stair handling real quick here. We still have a lot to do in this video, so we're going to make this quick. As you can see, we can go up and down stairs just fine here. We cannot go up anything that is higher than our max step height. This block right here is 1 unit high or 1 meter. This one here is half. Our max step height is a half. Oh, you can see it works perfectly, more or less perfectly. These stairs are half step high, half step deep. So your pretty typical average stairs. Let's go ahead and go up them. And you can see we can go up them just fine. We can stop on them. And if we go down them, and back up, stop, back up again. And we'll go all the way to the top and run off the edge to go back down. It's pretty decently controlled. If our angle of approach is greater than our max angle of approach to go up the stairs, then we cannot go up the stairs. So for example, right now we have it set to 45 degrees. So let's make sure our angle is more than 45 degrees. And we'll try to go upstairs. We cannot go up them. And also if our step is not deep enough, it does not meet our min step depth requirements, then we cannot go up the stairs. So for example, here we have a stairs, just very shallow stairs. It's more like a weird type of wall. And that's very basic stair detection and handling. If that's all you're looking for in this video, then you can stop there. If you understood the code so far, good on you. Otherwise, we're going to move on and we're going to tear apart the code bit by bit. I'm going to explain it in great detail. Hopefully by the end of it, you'll understand it pretty well. And after we're done reviewing the code, you might even want to just skip ahead to this part at the very least. But at the very end, we're going to do our playtest like this, except I'm going to show you a bunch of the bugs and problems with the code as it is right now, which believe me, there are plenty. But again, this is very basic, kind of crude, and not very good code, but it does work. All that said, this is a great base to start with. It shows you the idea and it gets you started. So I want to encourage you to take time to really understand this code and what is happening so that you have the knowledge to go in and modify it to suit your needs. Alright, so basically what we're doing is we're checking to see if there are stairs in front of or behind our desired direction of movement. And the way we're doing that, let me go ahead and make this little drawing for you quick. So here we have our player, we're looking at him from the side, and what we're basically doing is at the ground level, we are sending out a bunch of ray casts, spaced evenly between them. If they go out and they hit a wall that is 90 degrees, then they're going to check to see if on top of that, within the max step height, so right now we have that set to 0.5, but if this stair isn't higher than 0.5, at the very top of 0.5, we're going to send out another ray cast. This is our ray upper, and if this ray cast doesn't hit anything here and it goes far enough past our min step depth, then we're going to conclude that this is a stair. So again, all we're doing is we're checking to see if there's something here that is 90 degrees. If anything here is 90 degrees, then these raycast hits are going to get stored in the list, and then once we have at least one raycast hit that hits something here that is 90 degrees, we're going to send out another raycast. This one will be our ray upper check, and we're going to send out one of these, and it's going to check to see if there's anything up here. If there's not anything up here and there's room to step up, then we're going to try to step up. So it's really just that simple. These are the conditions that need to be met in order for this to be considered a stair. And with that basic idea in mind, let's go ahead and let's move to the code and start breaking it down. In the awake function, we have our max ascend ray distance and max descend ray distance variables getting assigned a value. This assignment of a value is being made a little more complicated than it needs to be, but you can see what you're doing here. Give me a second and I'll make you another drawing. Okay, so here we're looking down on top of our player and he's up against a quote-unquote stair. I guess you could consider this to be more of a stair. Anyways, this is the first stair right here, this line, and our player is right up against it. What we're trying to find out is the distance the player needs to send a raycast in order to hit the stair, given the maximum angle of approach to ascend. And all that means is basically this is the center of our player here. Our maximum angle of approach to ascend is 45 degrees, so we'll say that's a 45-degree angle. Our distance from the player to the actual stair, the shortest distance, is that distance right there. So here we have a triangle now. We know that this is always going to be a 90-degree angle, and we know that our maximum approach is 45. So what we want to know basically is we have a right triangle here, and we want to find out the length of the hypotenuse, which is this side right here. We want to know the distance of this side right here. Well, to find that out, all we got to do is figure out the cosine value, and then divide our max step height by the cosine. So that's actually all we're doing down here. First, we have to take our angle and convert it to radians. Conveniently, you can just use the mathf.degree to radius function. Now, I know this can sound complicated, but it's actually very simple. You can see the line right here. All we're doing is we're multiplying our maximum angle of approach to ascend by mathf.degrees to radius, which is just a number. It's like 0.017 if I hover over it. There's a number right there. All we're doing is we're multiplying that by our angle to turn it into radians. And then with our radians, we can then use the mathf.cosine function to find out the actual cosine from the radian value, and then we divide our max step height by that cosine value. That will give us our distance. Same thing with max descend ray distance, except with this one I didn't set a variable for some reason. I just put in 80 degrees. That's the maximum angle I want to concern myself with when descending stairs. It could be any number you want to set it to. I should actually probably make that a variable. I'm not worried about it right now. And then next we have our number of step detect rays equals mathf round int. We need a whole number. And what we're doing for that is we're taking our max step height, multiplying it by 100, getting half that value or dividing it by 2, and adding 1 to it. The reason we're adding 1 to it is because 0 is not technically a number, so we need to add 1 to get that extra number to it. And finally, we're getting our ray increment amount, which is going to be the space between our lower rays. And to calculate that, all we're doing is we're taking our max step height and dividing it by our number of step detect rays. Alright, let's scroll down to our fixed update loop. Here I just want to point out real quick that the order of these is very important. If you've been following along the series, it wouldn't really be necessary, I guess, for me to make mention of this because you'd understand how this is working so far. But in particular, our player stairs function does need to be called before our player slope function. And if we keep scrolling down, next we can review the changes that we made in the player ground check function. Depending on your game, this may not be a great idea, but I got rid of how far we're sending our sphere cast down to check to see if there's ground or not. And instead, we're going to send it an infinite amount down. So if there's ever actually a case where we're not hitting anything below us, this will actually cause problems and an error and ultimately cause the game to crash. Just putting that out there now. But anyways, we're sending the sphere cast down, same as before. We're using the same sphere cast radius. And now we have a global variable called player centered ground distance, and we're setting it to equal our ground check hit.distance plus our sphere cast radius. Finally, we're doing some checks to see if we're going to return true or false. Again, I know this looks complicated, but it's really not. We're just checking to see if our player centered ground distance is greater than or equal to our caps collider bounds extents.y, which is half our player height, minus our ground check distance tolerance, which is just a global variable that we set at the very beginning. So now that we know the minimum value, now we need to check to make sure that it's not extending past our maximum bounds. So we're also going to check to see if our player centered ground distance is less than or equal to our caps collider bounds extents.y, which again is our player half height, plus our ground check distance tolerance. If both those things check out, then we're going to return true, otherwise we're going to return false, our player is not grounded. We're going to end up talking about this just a little bit more in a little bit here. Moving on further down, we have our player stairs function here. We already talked about this quite a bit earlier, so there's not really much more to talk about here, but we did skip over the player half height to ground calculation, so we'll talk about that now. I'm going to take another second here to go ahead and make another amazing drawing for you. Alright, so here we're saying our player half height to ground is our caps collider bounds extents.y, which is literally half our player's height. So from here to here, this will tell us the distance, which in our case is 1.5 because our character is 3 units tall. Next, we're checking to see if our player center to ground distance is less than our capsule collider bounds.extents.y, and if it is, we are then setting our player half height to ground to equal our player center to ground distance. I'm going to try real briefly to explain why this is important, but basically nothing is ever perfect in a game world. When you're dealing with colliders and such, colliders will overlap other colliders, it's just how it works. So in this drawing up here, you'll see we have the ground, and our player is actually sticking into the ground a little bit. But we're sending out raycasts from the very bottom of our player to detect stairs, and if we're sending the raycast below the ground, that's not going to be very ideal. So what we want to know is we want to know the actual kind of true distance to the ground here. So what we're saying is if this distance is less than our actual player half height, then instead of using our actual player half height, we want to use this distance here, so that we are instead sending our raycast out where we want to. Likewise, if our player isn't perfectly on the ground and we're floating just slightly above the ground like this, we still don't want to send our raycast here. We want to send where our player actually is, up here. So that's why we're doing the initial setting of our player half height ground equals our capsule collider bounds extents.y. And then if and only if our player center to ground distance is less than our player half height, then we're going to say that our player half height to ground equals our player center to ground distance. So it's conditional logic that's basically limiting our player half height to ground to our actual player's true half height, and then lessening it if our player is actually sticking into the ground just a little bit. That's all it is, so let's move on down to our sendStairs function next. In our sendStairs function, first line, if our input.move is pressed, as mentioned before, we're just checking to see if our move key is pressed. If it's pressed, we're going to do all this, otherwise we're going to skip over it. This is not ideal in some situations. You may want to change this to something else, obviously. We've already gone over most of this, so I'm just going to go over the highlight points that I feel need to be discussed some more. I recorded this a couple weeks ago at this point, so I don't remember what exactly off the top of my head I already went over with the calculated veld distance. But I just want to stress again, this is not good code. There's better ways to do this. So I would encourage you to use one of those better ways, to discover one and use it. Otherwise, it does work just for testing purposes, obviously. But yeah, the idea here is that if this is the first step, we need a little more time to detect our stairs so we won't get hung up on it. So we're using a velocity factor to determine how much more distance we need to start moving our character up so that we don't get stuck on the stairs. Next, we're sending out all of our lower rays. It's just a for loop that's going to go through for the number of step detect rays that we have. Each time the ray is going to be a little bit higher up based upon our ray increment amount. We're sending the rays out in the direction of our player movement, and we're sending it as far as our calculated veld distance plus our max ascend ray distance. Scroll down a little bit. If this raycast hits another collider, then it's going to return true, and then we create a float called stair slope angle. This is similar to what we're doing with our actual slope detection. We're going to use the built-in Unity Vector 3 function called angle to find out the angle between our hit lower normal and our rigidbody transform up. Again, this is the same thing that we're using in our slope handling. So if you'd like more information on this and how exactly this works, I go into a lot more detail in that video. I would encourage you to check that video out. Here's what that video looks like. And once we have that stair slope angle, we're checking to see if it's at 90 degrees to us. If it is at 90 degrees, then we add it to our rays that hit list. Going down some more, if our rays that hit list has one or more rays that hit, then we're going to send out our single ray upper. And that ray upper is basically going to be sent out from the bottom of our player plus our max step height, so in this case 0.5, plus our ray increment amount. So it's going to be just one ray increment amount higher than all the lower raycasts we just sent out. Again, we're sending it out in the direction of our player movement, and we're sending it out as far as our max ascend ray distance times 2, so twice our max ascend ray distance because it's going to go higher, so it's going to go one more step further, plus our calculated veld distance. If this upper raycast did not hit anything with a collider, or if the hit upper distance minus the distance of our first ray that hit is less than our min step depth, so if it's within that margin, then we can step up. Otherwise, if there's something there, if that upper ray hits something, then there's obviously not enough room for us to step. It's probably a wall or something, so we're not going to step up. Or there's not enough room for our feet to step up it, basically. We're just checking to see if there's enough toe room for us to actually go up the stairs. Next, we're once again using the vector3.angle function to find out if the angle between our first raise that hits normal and the opposite direction of our player move input is less than or equal to our maximum angle approach to ascend. This is literally just getting an angle based upon our approach to these stairs to make sure that it's within the limit that we set, which was 45 degrees in this case. The trickiest part about understanding this one is the fact that we're using a negative player move input. I think it's simplest if I actually just draw this out for you as well real quick. Okay, here we have our player. Our player is moving in this direction. This line here is actually a stair. This is the first step or whatever. Doesn't really matter. Again, I explained what exactly the normal is in the slopes video that I did, but the normal of this stair, for example, is going to be perpendicular to the face that we hit. So in this case, the normal is this direction here. Again, perpendicular means that it's both two 90-degree angles here and here. And again, the reason why we have to reverse the direction is because we don't actually want this direction here. We want this direction here because we don't want this angle, which say this is a 45-degree approach. This angle here would be 135. We want this angle here, which is 45 degrees. Instead of doing the negative value, we could also just obviously subtract 90 degrees from this value, but it's just a lot easier to actually just reverse the direction and get it right the first time. We'll scroll down once again. Here we're creating a vector3 called playerrelx. And for its value, we're using Unity's built-in vector3.cross function. And for its input variables, we're using our player move input and our vector3.up. This is a pretty important part to understand, so we're going to dive into this a little bit here real quick too. So for this, let's go to the drawing board again. Alright, here we have our player. We're looking down on top of his head again. This is his center. He is facing this direction, but he's actually moving in this direction. So this is actually our player's X right here, and this is actually our player's Z, but that's not what we need to know here. We need to know the X-axis of our actual direction, which would be this here. And to calculate that, we're going to use our player's up, or our vector3.up in this case. You can also use your player's up, that's fine. So what the vector3 cross function does is it will literally take our player move input here, which again is this line here, and it'll take our vector3 up, which is this here, and it'll find the direction that crosses with. So basically, if we know two of our axes, the vector3 function will find the third one, because basically they're all just perpendicular to each other, right? So it's all just 90 degrees. Anyways, get all the square root out of the way, but basically when your x, y, and z all intersect, they're all perpendicular to each other, right? They're all at 90 degrees to each other. So if we know two of them, we can figure out the third one. That's what we're doing here, is we're just finding out the x-axis because we need to rotate our player based upon that, up or down, based upon our movement and not our player's current facing direction. This next little bit, this breaks a lot of things. I really don't like that I'm using a is first step boolean here. That should not be necessary. If I were to rework all this, I would make this work completely differently. And I really don't like even more that I'm using a hard value of 45 degrees here. This is just kind of patchwork to make it work. If you have different stairs with different slopes that are not all 45 degrees, then you're going to run into issues, which I'll demonstrate here in a little bit. But as I mentioned before, this is literally just creating a rotation value where we're taking our player rel x, which is our x-axis of our current movement direction, and not our player's direction, but our current movement direction. And we're going to create a rotation that will rotate it 45 degrees up. Then we're going to apply that to our player's current movement input, aka our calculate step input, and then we're going to say our calculate step input equals this new calculation. And then if we scroll further, this is the most common case. After the first step is no longer a thing. Then we're going to come through and we're going to figure out the stair height, which this is also not a great way of doing this. We should actually just be recording the ray value of our ray lower so that we know the actual height, because this is assuming solid stairs. For something like a floating stair, this will cause problems. We will not get the correct height value back. But anyways, if you have solid stairs, this will work just fine. And to find our stair height, we're using our raise that hit dot count times our ray increment amount times our stair height padding multiplier. This padding multiplier can be a much lower value. I think I have it set to 1.5, but this will probably work just fine with anything around 1.1 or 1.15. Around that value should work just fine. The reason we need this is because we're treating this like a slope, but our player's collider is actually a capsule. It's not a slope, so it's a rounded surface at the bottom. Well, actually, instead of visualizing it, let's just draw this out real quick as well. Alright, so here's another terrible drawing, but I just want to give you an idea. So our player obviously is a capsule collider, which means he has a semi-sphere at the bottom of him, and we're trying to go up basically a square staircase. What that means is if we were to plot a perfect angle from here to here, which would look like this. And obviously we're going to have some overlap, so when our player gets to this point here, he's going to start to rub and he's going to bounce every time he hits this point. It's going to slow him down, it's going to cause bumpiness, it's going to cause choppiness. It's not really ideal, it's not really what I was going for with this. So what we do is we add a little bit of a buffer to the top of this to move this up, set this angle, comes up higher. And instead, what we end up doing is we end up doing a path more like this. Now obviously this isn't the best way of handling this. We're just applying a static number to handle this issue. What we should be doing is we should be taking into account our semi-sphere shape here and use that to calculate the angle necessary to clear our stairs all the way up, but I didn't want to get into that in this video. Anyway, moving along here. Now that we've calculated our height, we know how high our player needs to go here. We now just need to know how far away our player is. So for that, what we're doing is we're taking all of our raycast hit distances. Some may even hit this one here. And we're going to take them all and we're going to loop through them and add them all together. And we're going to divide that by the number of rays that hit. That way we get an average distance. And now that we have the backing of the stair and how far away we are, we can now find out the tangent angle, which is this angle right here. And that's what we're doing in this next line. Is we're creating a float called tangent angle, and we're using the mathf.atan2 function to use our stair height and our average distance to find out how many radians are in our tangent, and then we're converting our radians to degrees. Finally, same as before, we can then modify our calculate step input with the quaternion.angleAxis function, except this time we're going to use our tangent angle, and we're going to modify our player rel x, same as last time, and then we're just going to multiply that by our calculate step input to actually modify our calculate step input. And then the last line here, finally, as I said before, we're just going to take into account our ascending stairs movement multiplier. And just to backpedal, make that just a little bit clearer here. So say we have our player here, and we know the angle we want is this one here, but our player is moving this way. If we get the angle, and we apply it to our movement vector, and we have the same angle, then we're going to have the angle of movement going perfectly up the stairs. I know I explained things quite a few times. I try to explain them in different ways so that hopefully one of them you understand, even though sometimes I feel like I just end up with a bunch of scribble. And let's go ahead and clear this board. Next, let's go down to our descend stairs function. Our descend stairs function is very similar, except we're not using the is first step boolean anywhere. We've removed that. We're also not checking in front of us, but we're checking behind us for stairs, and we're also checking further out, which may or may not be a great idea. Honestly, I didn't put a whole lot of thought into this, but this is pretty much exactly the same as the ascend stairs function, just reversed with a little further distances, and it doesn't have the is first step boolean. Alright, now let's talk about the bugs and the problems that we actually have with the script. As I mentioned earlier, we're not actually calculating our step height properly, so if there's no backing for the step, or the step doesn't have the full thickness or height to it, then we're not going to calculate it properly. We're not taking into account the ray and its position relative to our player. We're just getting a number of rays that hit and assuming that every ray that hit is the actual stair height. That's not the case. So when we go up stairs that are actually floating, like these ones here, you'll see when we go slowly, we actually hit every step and we don't float high enough above it to avoid this. If we run, the capsule collider will basically just kind of skip over it, but it's still not the smoothest. Anyway, that is a glitch. That's something that can easily be solved if you need it to be. Additionally, if you remember, I was complaining about the is first step. We're assuming that if it's the first step, that it's a 45-degree angle that we need to take. So when we go over these very shallow steps, if you can even call them steps, but they still have a 90-degree surface that is being hit by one of our rays, so our player is going to treat them as stairs. When we go over one of these shallow stairs, regardless of it, we're going to have that problem where our player is going to skip because it thinks it's the first step, and it's going to do that one physics frame where we're altering our player's movement 45 degrees up. The next problem we're going to have with our descending stairs method is this right here. You'll notice if we go up these stairs and we go off the back of them, instead of us falling, it actually acts like we're descending stairs. Whereas what should happen is we should just go off and it should just fall like that. So that's an obvious glitch. That's something that needs to be fixed. Additionally, we're also getting some strange behavior when we're going up these shallow steps. Even though we technically should not be able to go up them, except for maybe at an extreme angle where we're actually getting just enough toe room. But there's obviously something wrong with how we're detecting it. Maybe our raycasts are going all the way through. I'm not sure. And then finally, again, I think this is another issue with our is first step, assuming 45 degrees. But you'll notice that on this platform, we have all these different distances. And if the distance is just right, you'll notice that by the time we come back down on the ground again, we actually hit the edge of the next step, and that hangs us up for a second. Obviously, that ideally should not be happening. Anyway, those are the main issues I've noticed with the script so far. There are a lot of issues with inertia causing the player to skip down the stairs faster than he's really supposed to when no movement input is being applied. This is due to gravity and the stairs being frictionless. There are a lot of ways to deal with all of these issues, and I'm sure I'm forgetting a few issues and haven't even noticed many others, but I think this is plenty for one video, and so I'm going to wrap this video up here. I've had a lot of fun playing with the stair handling, and I hope you do too. Sorry I didn't have enough time and interest to make this better, even though I really wanted to. For now, I'm happy with this basic, though flawed stair handling until I have time to revisit it. As always, if you have any questions, please ask them in the comments. I hope you found this informative and helpful. Let me know if you learned anything or found anything confusing. My real life has been significantly busier than usual, and this video ended up being a long one. Combine those facts, and that'll explain why it took so long to get this one uploaded. I hope it was worth the wait to some of you, though I feel bad it's not better quality. For the foreseeable future, new uploads will be much shorter videos and simpler topics. I hope this will help allow me to keep adding new videos relatively consistently. That said, in the next video, I believe we're going to give our character the ability to crouch. Looking forward to it, and I'll see you then. If you're feeling generous, leave a comment down below. I want to read what you're thinking. Let me know if you have any questions or recommendations. I'd also appreciate it very much if you liked the video. And if you're feeling extra generous, it'd blow my mind if you subscribe to the channel. Being new to this and putting these videos together takes a lot of time and effort. Thank you for any and all participation and support. I look forward to continuing this in the next one. See ya.